For number 4, this is a inventory problem. So what we need to do is set up a cost function, because the problem asks you to actually find a number of cases to minimize cost. So first thing we need to do is let x be the number of cases that the firm should order each time, because that's exactly what the question is asking. And once we have that information, then we can calculate the amount of shipments based on that variable. Since altogether the company needs to order 2,250 cases in the entire year, and each time they're ordering X cases, therefore the amount of shipments that the company is going to have is the total amount divided by X. Therefore the total cost function, which is represented by C of X, is a sum of the overall cost on different categories. So the first category is the purchase fee. The second category is the ordering fee. And the third category is a storage fee. For the purchase cost, since each case costs $900, and altogether we're going to be ordering 2,250 cases in the entire year, therefore we're just going to spend $900 times 2,250. For the ordering fee, since it's $15 per shipment, and altogether we have 2,250 divided by X shipments in the entire year, we're going to be spending 15 times 2,250 divided by X. For the storage cost, what we need to do is figuring out what is the number of cases are actually in storage at any given time in the entire year, and multiply that number by $0.75. So for now, we're going to assume that we know that the number of cases on average in the entire year is x over 2. And that is something that we derived in class before. But in case that you're wondering about that, I'm going to explain how to get that x over 2 in the next page, after we finish this problem. So the storage cost is simply just $0.75 times x over 2. If you do the math on these multiplications, we get the following equation. So to minimize the cost, we're going to use the derivative tests, which is one of just the standard optimization problem. I'm going to take the derivative of the cost function. So the first term goes to 0 because that's just constant. The second term, when you take the derivative of it, because it's written as 33,750 times x to the negative 1, so when I take the derivative of it, I'm going to bring the negative 1 down, and then the x term becomes raised to the negative 2. But then to rewrite that negative power into positive power, it becomes the division over x squared. And for the third term, is simply just a power. So that's 0.375. We're going to set that equal to 0 and solve for the x value as a critical point. So moving the fraction term to the right and leaving the 0.375 on the left gives us this equation. And divide and then multiply everything by x squared helps us reach this equation. And once we have that, we can divide it by 0.375 both sides, which then gives us x squared equals to 90,000. Square root both sides, we get 300. And remember that when you take square roots, supposedly you get plus and minus. But because we're dealing with the number of cases, which is always a positive quantity, therefore we're going to drop the negative signs. And remember that you always have to verify that this indeed gives rise to a minimum. So we're going to take the second derivative on the cost function. So the second derivative from the cost function gives us 33,750 divided by x cubed. And when you plug in x equals 300 in that expression, you'll see that this quantity is always positive, which means that your function is concave up. If it concaves up, that means it reaches a global minimum. Therefore, we've verified that this indeed gives rise to a minimum. Hence, we're pretty much done with the problem. The firm should order 300 cases each time. Now next, I'm going to try to explain why the number of cases during a year is on average x over 2. So this is called a just-in-time inventory. So here, the following is a graph that describes the number of cases in storage at any given time. So if we plot on the x-axis the time, and on the y-axis the number of cases we have in storage at that given time, then in the beginning of the year, when its time is equal to 0, we first order it, a shipment, and at that time we have x boxes in storage. As time goes on, the rate at which the cases that's being used is decreasing at a constant rate, therefore explaining the kind of a linear behavior going downward to reach the x-axis 0. And once you have used up all of the cases, you're going to order again. So that's when we reach 0 on the x-axis, and then it just kind of jumps up again because you order another fresh set of cases. And you just repeat this process every time you use up something. You just order a new set again. So over the entire period of time, you would have the number of boxes in the storage would be the shaded area inside these triangular regions. And that's for the entire year. So then the question is, how do you actually calculate the area of these shaded regions? Well, that's simply just the area of the triangles. So the sum of these shaded area would then be the 1/2 times base times height. And the base is some period of t, and the height is x. And that's the same for all these triangles. I only drew 3 because that's convenient for me to do. It could be as many as needed, but the idea is the same. So if you actually factor out 1/2 x from all of these terms, we're left with the sum of these t's. But because this is over the entire year, so we know that the sum of those little t's should add up to 1. Therefore, we get the expression of 1/2 x times 1, which is half x. That explains why, at any given time, the number of cases that we have should be x over 2 during the year.